At this exact moment, something extraordinary is happening on a distant ice ball, nearly 6 billion kilometers from the sun, deep within a glacier roughly the size of Texas and Oklahoma. Combined liquid nitrogen is forcing its way upward through fractures in the ice. The surface temperature here hovers around minus 230 degrees. The world is smaller than our own moon. And, according to everything planetary scientists believe for decades, it should be nothing more than a dead frozen chunk of rock with no internal heat whatsoever. That world is Pluto. In August 2026, a research team headed by Alan Stern, the lead scientist behind the New Horizons mission, released a peer-reviewed paper confirming something that shouldn't be happening at all. Liquid is actively pushing up through Pluto's iconic heart-shaped glacier right now. Not eons ago, not in some ancient geological chapter. Today. For years, nobody seriously questioned what kept Pluto warm because the assumption seemed self-evident. It shouldn't be warm at all. Yet that assumption is now unraveling into one of the most compelling mysteries in planetary science. The explanation traces back to a nuclear process that has been humming along for 4.5 billion years inside a body long written off as geologically dead. Consider the numbers. Pluto orbits at an average distance of 9 billion kilometers from the sun, where sunlight arrives about 1,000 times fainter than it does on Earth. Its atmosphere is so thin that breathing would be impossible even without the lethal cold. With a diameter of roughly 2,377 kilometers, Pluto is smaller than Earth's moon, and objects that small are expected to lose nearly all their primordial heat within their first billion years. This isn't guesswork. Small bodies have a large surface area relative to their volume, so they radiate heat away quickly, which is exactly why the moon is geologically inactive and why Mars shows far less activity than Earth. Following that logic, Pluto should be a solid, inert ball with no liquid, no volcanism, no internal motion of any kind. That was the scientific consensus for decades. Then, in July 2015, NASA's New Horizons spacecraft flew past Pluto and upended everything. The images revealed towering waterous mountains reaching several kilometers high, nitrogen glaciers visibly flowing across the landscape and dune fields sculpted by wind in an atmosphere scientists doubted could even move surface material. There were ice volcanoes, too, Wright Mons, standing about 4 kilometers tall with a crater-like depression at its peak, and the even larger Piccard Mons rising. Some 7 kilometers, one of the most massive cryovolcanic structures relative to its host world, found anywhere in the solar system. Most striking of all was Tombaugh, Regio, the famous heart-shaped region of bright nitrogen ice, whose western section, Sputnik Planitia, turned out to be among the youngest and smoothest surfaces ever observed in the outer solar system. New Horizons team member Jeff Moore remarked afterward that Pluto rivals Mars in complexity, a startling claim given Mars's volcanoes, canyons, and billions of years of geological history. But the data backed it up. So what's driving all this activity? The buried liquid, the flowing glaciers, the erupting cryovolcanoes, the youngest terrain in the entire Kuiper Belt. The answer is radioactive decay. Pluto's interior heat comes from unstable elements, chiefly potassium-40, along with uranium-238 and thorium-232, that were locked into the planet's rocky material when it formed from the same primordial cloud that built the whole solar system roughly 4.5 billion years ago. These elements release energy slowly as their nuclei break down over time. Potassium-40 has a half-life of 1 to 25 billion years. Uranium-238 is 447 billion years. This isn't a burst of energy, it's a steady, uninterrupted trickle of nuclear heat that predates Earth itself. As long as Pluto's core contains at least about 100 parts per billion of radioactive potassium, a perfectly ordinary amount for rocky solar system material, this mechanism can sustain liquid water, placing Pluto alongside other outer solar system bodies suspected of harboring subsurface oceans. The structure of Pluto makes this possible. Scientists believe Pluto is differentiated, meaning that early in its history, heavier rocks sank toward the center, while lighter ices rose toward the surface. This left a dense rocky core surrounded by layers of water, ice-topped with an outer crust of nitrogen, methane, and carbon monoxide ice. That rocky core is where the radioactive material and the heat it generates is concentrated. That warmth spreads outward into the surrounding ice shell, which acts as insulation, keeping a subsurface ocean liquid. That ocean is largely water, but mixed with ammonia, which acts as a natural antifreeze. While pure water freezes at 0 °C, an ammonia-water mixture can stay liquid down to roughly 100 °C, in some proportions, dramatically widening the temperature range, in which Pluto's ocean can persist, even as the core's heat output gradually declines over billions of years. This finding hints that hidden oceans may be far more common throughout the outer solar system than once believed. While early Earth was still a molten world covered in seas of magma, Pluto's underground ocean was already forming, and it has persisted largely unnoticed ever since potentially offering a distant refuge where life could exist. The most recent chapter in this story may be the most remarkable yet. The August 2026 study led by Alan Stern's team working with the Southwest Research Institute found evidence that liquid nitrogen is currently forcing its way up through fractures near the northern edge of Sputnik Planitia, the first evidence of liquid actively flowing on Pluto's surface in the present day, or having done so recently enough that the resulting surface marks remain geologically fresh. The researchers examined dark, narrow linear streaks and broader, hazy patches in that northern region, and compared them to similar dark wetting patterns observed on Greenland's ice sheet, where liquid water rises from below and darkens the surface ice. The resemblance was compelling. Their modeling showed that liquid nitrogen could travel upward through small channels, much like lava tubes or geyser conduits, and stay liquid long enough to leave these dark markings before refreezing. Sputnik Planitia's surface is thought to be less than 1 million years old based on estimates of how frequently the ice overturns, meaning any features that formed since then count as recent by geological standards. Stern noted that Pluto keeps finding new ways to surprise researchers and that this discovery is no exception. Beyond confirming recent liquid activity, the findings point to an entirely new category of feature. On Pluto, one that changes over time on scales that are essentially instantaneous in geological terms. The mechanism is basal. Melting heat rising from below is warming the underside of the glacier. That heat traces back to the same radioactive decay process that has been running in Pluto's core for 4.5 billion years. The chain runs like this radioactive isotopes in the rocky core. Decay and release heat. That heat warms the ammonia-laced ocean above the ocean. Stays liquid. That warmth in. Turn heats the base of the kilometers thick nitrogen glacier from below pressure and temperature at that boundary melts solid nitrogen into liquid, since the liquid is slightly less dense than the surrounding ice. It rises, finding cracks to travel through, much like water moving through porous rock. When it reaches the surface, it darkens the nitrogen ice, producing exactly the patterns Stern's team identified and matched to Earth's glaciers. All of this is happening on a world 6 billion kilometers from the sun, powered entirely by nuclear decay. Right Mons, roughly 4 kilometers tall and 150 kilometers wide, is composed mostly of water ice with a deep depression and at its summit resembling a volcanic caldera. Structures like this suggest Pluto's interior may retain heat more effectively or generate more of it than scientists expected. Before New Horizons, Picard Mons, even taller at about 7 kilometers, tells a similar story. Both formations show remarkably few impact craters. A strong sign of geological youth, since a heavily resurfaced area hasn't had time to accumulate new impacts. In March 2025, researchers at NASA's Jet Propulsion Laboratory identified a possible new cryovolcanic feature northeast of Sputnik Planitia, dubbed the Kaladze caldera. Unlike the largely methaneric terrain surrounding it, this site shows a waterous signature containing ammonia compounds, chemically similar to 2 other known cryovolcanic sites on Pluto. That ammonia-infused water ice is essentially a signature of material erupted from deep within Pluto. A water-ammonia slurry from the subsurface ocean that reached the surface and froze physical evidence of the planet's internal nuclear engine at work. Despite sitting at a frigid 40, Kelvin Pluto shows genuinely active geology and a shifting atmosphere, making it a model for what active icy worlds elsewhere in the distant solar system might look like. That last point may be the most consequential scientific takeaway of all astronomers. Long assumed the outer solar system was little more than a collection of frozen, inert leftovers from planetary formation. That picture is rapidly falling apart. The evidence of active basal melting on Pluto paired with signs of internal heat on the dwarf planets, Eris and Makemake and the known geysers erupting from Neptune's moon, Triton builds a strong case that this region is far more dynamic than its extreme cold would suggest. Triton vents material into space. Pluto pushes liquid nitrogen through its glacier Eris, and Makemake both show hints of internal warmth. The Kuiper Belt, once considered a frozen graveyard of ancient debris, increasingly looks like a collection of geologically living worlds, all quietly powered by the same radioactive processes that have been running since they formed. In April 2026, a 10-year-old from Tampa, Florida, named Kayla Polkinghorne wrote to NASA asking that Pluto be reclassified as a planet, laying out her reasons politely, and more than once, NASA Administrator Jared Isaacman responded personally within hours on April 9th, saying the agency was looking into it. This wasn't just a courteous reply to a child. At a Senate Appropriations Committee hearing on April 28, 2026, Isaacman stated he personally supports reinstating Pluto's planetary status and that NASA is drafting formal papers. It hopes to bring before the broader scientific community to reopen the debate. The push isn't rooted in nostalgia, it's grounded in the science. The International Astronomical Union's 2006 criteria for planethood require that a body orbit the Sun be massive enough to pull itself into a roughly spherical shape, and have cleared its orbital neighborhood of other debris. Pluto satisfies the first two, but fails the third since the Kuiper Belt contains numerous comparably sized bodies that Pluto's gravity hasn't dominated. Critics of that standard point out its inconsistency. Some argue Pluto's complex active geology should matter more than whether it shares its orbital region with other objects. And the comparison holds up under scrutiny. Earth coexists with roughly 10,000 nearby asteroids, and Jupiter shares its orbit with about 100,000 Trojan asteroids. Under a strict reading of the clearing, the neighborhood rule, neither Earth nor Jupiter fully qualifies either. Adding to the controversy, the 2006 IAU vote was decided by only a small fraction of the organization's total membership cast during the closing days of a conference, and it has remained contentious within the scientific community ever since. A growing number of planetary scientists now argue that a body's internal structure, active geology, atmosphere, and surface dynamics are more scientifically meaningful markers of planethood than pure orbital mechanics. By that standard, Pluto qualifies unambiguously. It has a layered interior with a rocky core, a liquid subsurface ocean, and multiple ice layers, active geology powered by internal nuclear heat, a seasonally shifting atmosphere, mountains, glaciers, dune fields, nitrogen winds, and cryovolcanoes, and a moon cairn so large relative to Pluto that the two bodies orbit a shared point in space between them, a configuration unlike anything else in the solar system. Isaac Mann has said NASA intends to bring this case formally before the scientific community, while the IAU maintains that classification decisions require international consensus built on evidence. As of April 2026, Pluto's official 2006. Classification hasn't changed, but the fact that a sitting NASA administrator is formally advocating for reconsideration backed by New Horizons data elevates this from sentiment to a genuine institutional and scientific question. There's a certain poetry to the timing. The August 2026 discovery of liquid nitrogen actively rising through Pluto's surface is only the latest in a string of findings that have steadily dismantled the assumptions that justified demoting Pluto in the first place. It was assumed to be geologically dead wrong, assumed to have no subsurface liquid wrong, assumed to be a simple inert object wrong, assumed that only the inner planets could host complex geology also wrong. What New Horizons revealed in 2015 and what scientists continue to uncover as they revisit its data more than a decade later is a world that has earned its complexity through the oldest, most dependable energy source. In the universe, the slow decay of radioactive atoms, a process that began before the solar system took its current form and has never stopped. It is still at this very moment melting the underside of a nitrogen glacier 6 billion kilometers from the sun and forcing liquid up through cracks to the surface on a world once dismissed as too small, too cold, and too remote to matter. Pluto isn't a frozen rock. It's a nuclear-heated, ocean-bearing, cryovolcanic, glacier-flowing world with a real atmosphere and active geological processes that researchers are still uncovering new evidence of in 2026. It rivals Mars in geological complexity and Europa in scientific intrigue, and it stays warm through a nuclear reaction that will keep running for billions of years to come. Whether or not the International Astronomical Union ultimately sides with NASA's administrator, the data have already answered the more fundamental question. Pluto is alive, and the nuclear fire lit in its core. 4-5 billion years ago has gone out since.